This is section 9.3, the integral test in the P-series. Let's recall in 9.2, when we examine a series, right? So when you say a series, it's really the sum of an infinitely many terms in a series, okay? And how do we check whether a series converge, diverge? The first technique is we just using the definitions. So what it means is we're gonna look at the impartial sum as Sven. And then once you figure out the impartial sum, we're gonna take the limit of the impartial sums and approach infinity, right? So that's the first way to do. Now this is not always achievable and it's hard to do. So we're going to develop some tests so we can quickly determine whether it converges or diverges. The first test we have is called the divergent test. All right, the divergent test. And for the divergent test, we take the limits of a sub n, right? So the limit of a sub n and approach infinity, and if that one's not equal to 0, then it diverges, right? So that's how we do. And then we have another test or special type of series called the geometric series. Geometric series. So if we have geometric series, then we have the way to determine it, whether it converges or diverges, based on whether the common ratio thing has the form, looks something like this, and based on the R. And then the fourth one is the telescoping series. So for the telescoping series, we're actually using the definitions here, but we have to do the partial fraction decompositions there. Now today we learn the fifth test is called the integral test, right? So throughout this chapter, we'll develop more and more tests to use, and then you can identify which one to apply to determine whether a series converge or diverge. Okay. Now let's get into the integral test. All right, so if you look at the integral test, it's a statement. If we have a sub n is a positive sequence and a sub n equal f sub n, with f of n is continuous positive decreasing functions, then the series we test and this improper integral from n to infinity both converge or both diverge. In fact, the capital N here could be any integers. Okay, so it could start at 2, at 3, at 5. It really depends. So sometimes the series start at 1, so it could be 2, 3, 5. All right. So what is this series? Well, what does this mean? So basically, what it means is instead of looking at the series, you're looking at the functions. Now, the functions here have f of n equal a sub n, meaning the series, the term of the series and the functions are actually the same. So that means the formula will be the same. Okay, so if you have a sub n, let's say the formula for a sub n is 2 over n squared, then the functions f of x will be 2 over x squared. So see this one and that one, they are the same formula. That one in terms of n, that one in terms of x, difference. The n here, don't forget, is constant, the positive integers, be 1, 2, 3, so on. What is the x? X is all real numbers, In this case, I think it's all real number but cannot be 0 there, right? So this the domain is negative positive infinity except 0. Now, if you're going to grab both of them, the left side, the sequence, if you graph, will be a series of dots, while the function here will be a continuous function. It might be discontinuous at some point, but it's going to be a curve. Let me make a quick sketch of these two so you can compare. Now look at this. If we're going to graph the sequence here, 2 over n squared, right? So when n is 1, I plug in 1, and 2 over 1 squared is 2. So we've got here 1, 2. When n is 2, when n is 2, is 2 squared is 4, so 2 over 4 is 1/2. I think that one is off, so it's gonna be 1/2. So it's gonna be down here is 1/2, right? And then when it's 3, then 2 9, so it's gonna be down here close to 0. And then 2 over 16, so it approach the x-axis very quickly, right? 0. So if you grab the sequence, it's going to be this, 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 this. Now, if you're going to grab the function f of x2x squared, basically you plug in x will be 1, 2, 3, 4, 5. You're going to get these, but because x could be anything, so when you graph the function f of x equal to x squared, you will end up with this, right? Remember, we connect the dots and it is a continuous function. So it's going to be going through. In fact, I think it has vertical asymptotes over here. So we actually have the other branch go like this, right? But looking from the right, on the right only, you see that the curve goes through the dots, right? Now, this test saying if we're gonna do this function f of x over 2 equal to x squared, like this function here, if this function is set by 3 conditions, continuous, is it continuous? It's not continuous at 0, right? But because we are concerned about the series actually from 1 on, so definitely from 1 on, the function is continuous, right? So that one check. Not all the time, but list on the right-hand side the x-axis of the y-axis, right? So that's continuous. Is it positive? Yes. Again, from 1 on, you see the graph is above the x-axis, so always has positive values. Is it decreasing? Well, that is clear. You see this approaching the x-axis getting smaller as x increase. So these 3 conditions actually check, particularly the conditions here if x is greater than or equal to 1. So if you have these 3 conditions satisfied, then the test says the series that you want to check will converge or diverge depends on whether this integral converge or diverge. So remember from 8.8, I think the improper integral, that's improper integral from n to infinity. In this case, it doesn't matter, but if say from 1 to infinity, say from here, so this integral represents the area underneath the curve. So we're talking about this area, right? So if you're gonna find this integral, if that approaches infinity, that diverge, that series diverge. If this integral converge, that series converge. So we kind of use the integral as a gauge, a tool to gauge whether the original series C converge or diverge, right? So let's look at an example here. Does this series converge, right? So that's 1 over n root n, okay? So again, what we're gonna do is look at this. Well, we're gonna find a function, so we need to find a function that has the same formula as that one. So what is it? F of x is going to be 1 over x root x. Okay, so we will focus on the functions 1 over x square root of x. Okay, I consider these functions 1 over x root x. Then I'm going to check whether these functions is continuous, positive, and decreasing. Check 3 conditions. Okay, so are they satisfy these 3? Well, if you look at this function again, it's always continuous if x is positive. Notice that if you have 0 at the bottom, it's not continuous. So if x is greater than 0, the function here is continuous. Is it positive? In general, no, right? Because it could be negative, but again, when x is more than 0, then if you plug in any positive number here, you do the math, it's going to end up with a positive value. So it's always positive. Is it decreasing? Well, it's easy to see because 1 is on the numerator, it's constant. The denominator is contained variables. If x getting larger and larger, the fraction getting smaller and smaller, so that's decrease. So in this case, it's easy to check the 3 conditions are met. And when these 3 are met, we will consider the the improper integral. Okay, so I'm going to look at the improper integral of these functions, 1 over x root x. See, that looks like this. Same, except sum, that will be your integral. You see the same here from 1 to infinity. Right, so we're going to integrate this. Right, so let's recall, by definitions, when you want to integrate the infinity, you have to replace it with arbitrary b. Then you take the limit b approach infinity. Okay, so we'll do that. Now, to integrate this function, I'm going to rewrite this. X is first power, that's a half power. So 1 and a half combined, the denominator could be written as x to 3/2 power. And when you rewrite that without the fraction, that's equivalent to x to the negative 3/2 power. Okay, so from here I can integrate, right? So this is the power rule. You add 1 to exponents, so that's x to the negative 1/2. Add 1 to it, 1 minus negative 3/2 is x to the negative 1/2 divided by negative 1/2 or times negative 2. Right, so we have the lower limits of 1, upper limits arbitrary b, and plug b in. And don't forget that here you might rewrite it. X to negative half is equivalent to what? That's half is square root. Negative, so be in the denominator, so it would be negative 2 over square root of x, right? So that is this. Then you plug b in, you plug 1 in, then we have negative 2 over root b minus, and then you plug 1 in, negative 2 over 1. So minus a negative 2, it turned into a positive 2. And then finally, you take the limit and b approach infinity. So you see that this will approach 0. That approach 0 as b go to infinity. So this integral equal 2. So what that means is the area underneath the curve 1 over x root x from 1 to infinity will be 2. Therefore, the integral converges. Since this integral converges, the original series must converge by the integral test. Okay, since the integral converges, the series must converge, but not necessarily to 2. So by that, I mean the sum of the term in the series not 2. The area underneath is 2, but the sum of the terms is not. necessary to. I don't think it's 2, it's much smaller, right? So again, make sure that you check the 3 conditions, find the improper integral, and we'll determine whether it converges or diverges based on the answer we got here. Now let's look at the next example. Determine whether the series convergence or divergence here. Okay, so if you look at that one, here's the first one. Again, maybe you want to label it. It's example 1. Now, if you look at example 1 here, I have that sequence, right? Series 1 over n. To apply the integral test, I look at the functions f of x equal, same formula, 1 over x. And I'm going to ask myself, is this function continuous? Condition 1. Continuous? Is this function positive? And is this function decreasing? Check 3 conditions. Now, since this function has only 1 on the top and at the bottom, it's easy to see. It's continuous as long as you don't have 0, right? So I'm going to write this for, notice that n is bigger than 1. So how about I say, if x is greater than equal to 1, right, then this is always continuous. It's always positive because now x is more than 0, right? So positive, and it's always decreasing because n getting large, fraction getting small. So these 3 I check, and then I look at the integral from 1 to infinity, 1 over n, sorry, 1 over x. 1 over x dx. Right, so again, by definitions, that's the same as a limit, and then the integral from 1 to b approach infinity, 1 over x dx. Don't forget that improper integral there. And then from here, I can integrate this. I think it's easy, right? That I can do it directly. It's 1 over x plus natural log of x. Natural log of x, right? B approach infinity from 1 to b. Well, I can plug in b, so that's natural log of b, and then to subtract, what you subtract the natural log of 1. Right, so minus natural log of 1. B approach infinity. Now, when b approach infinity, the natural log go to infinity, that's go to 0, so that equal to infinity, and therefore this integral diverges, and that implies the original series that we checked diverges, okay, by the integral test. All right. Now, if you look at the second example here, this is number 2. We do the same thing. You're gonna look at the functions f of x equal, what is this? 1 over root x, right? These functions. And then again, you ask yourself, is this function continuous, positive, and decreasing? And do the example, that's harder, but this one again is very obvious. It will be true. I think they are true if x greater than or equal to 1. Then it's continuous, it will be positive and decreasing. And again, you're going to consider this interval integral from 1 to infinity, 1 over root x dx. Once again, by definition, that is the limit of integral from 1 to b, 1 over root x. Now, to help integrate this quickly, now we don't have 1 over x and 1 over root x. Then you have to rewrite that as x to the negative 1/2 power. So we can use the power rules there. Right? Using the power rule, I have x to the, add 1 to the exponent, so that's x to 1/2 divided by 1/2 or times 2. Right? From 1 to b, we approach infinity. And now I have plug in b, right? Plug in b, you have that's 2 square root of the square root b minus plug 1 in, well, that's 2 times 1 is 2, and b approaching infinity. Now, in this case, what happens when b go to infinity? Oh, that's go to infinity as well, right? Square root of b getting larger and larger, and therefore I got the infinity again. And that means the original series diverge again. All right, so they both diverge in this case. Now let's observe the patterns here. Look at these two examples. We have 1 over n, 1 over n, and these two cases diverges. If you recall back to the last example we did, is the what's the one, the series 1 over n root n in the previous slide, right? And that series turned out to be a convergent series. It converges. Now, if you look at all three, they actually have one in common. Actually, you can see the 1 over n root n, this is n to the first, that's n that I have. So if you simplify, that turned out to be n to the 3/2, right? So you're going to have n to the 3/2 here. And that is n to the first. And then for this series right here, if you rewrite it, it becomes 1 over n to 1/2 power, right? So if you look at all three, they actually belong to the same type of series. They are all 1 over n to some kind of power that is 1, that is 3/2, that's 1/2. Now, when you do this using when you check the series using the integral test, they are basically relies on the integral, right? Now, all of these functions, if you graph, they have the same type or similar graph. Now, I have the graph of these three series, or the three corresponding functions. The 1 over x, 1 over x to the half, and 1 over x to the 3/2. Now, because they all relies on the answer of the improper integral, and the improper integral actually represent the area underneath this curve, right? So what happened is you see the 1 and 2, the blue and the purple, they diverge. Well, it's just because the graph underneath, the area underneath the blue and the purple is big. So it's going to be infinity. Now, when the power is getting larger, like 3/2 of 1.5 here, you see that the graph goes to the x-axis pretty quick. So that make the gap here, the area underneath is really small. So when it's really small, then the area here is finite, and therefore the integral converge, and that means the original series here converge. So you can see if I change the problem, say is a number 4, what's the integral of 1 over n to the third power, right? So what happened is then your graph 1 over x cubed, we do the integral test, it's going to be like this, but it decreases 0 very quick. So the area even smaller. So it's smaller, so the area is finite, therefore this is to be converges. So in short, by looking at just the power of these, see this 3 is 1.5, it's 1.5, we can determine whether 0 converge or diverge quickly. In fact, the 1 over n, which is the first power, is this purple here. These are the borderline, right? So if you have any power 1 over n, where n is less than 1, like a half, a third, then your graph will lie above, and so it will diverge. If you have the power p in 3/2 or 3 or 4, it's the graph will lie below this purple, and so the series will converge, right? So that leads to the following p series test. It's really come from the integral test, but kind of a shortcut now. We can use the shortcut T from now on, right? If you have a series of the form 1 over n to the p, n equal 1 to infinity, so that means you can have the form 1 over 1 to the p power, 1 over 2 to the p, and etc. If you have that series, then we know that series converges if p bigger than 1 and diverges if p less than equal to 1. So if you look at the one that we have, this is 1, right? This is a half. So if the power p is 1 or half, so less than or equal to 1, then this series diverges. If you look at the power p is more than 1, or 1.5 or 2 or 3, then the series would converge, right? Again, the convergence of this p series follow directly from the integral test. Right, so that finishes the first part of the 9.3.